So first of all, being the last speaker of this workshop, I would like to express also on behalf of all the participants a deep gratitude to the organizers for putting together this wonderful community in a wonderful within a wonderful environment. So with my talk, I would like to share with you some recent and beautiful results that have emerged in the community of atomic physics concerning the phenomenon of supersolidity. And so what is a supersolid? A supersolid is a system which exhibits both superfluid and crystal feature. And this is a non-trivial situation because it requires the spontaneous breaking of two different symmetries. The so-called phase symmetry giving rise to superfluidity, and the translational invariance, which provides the typical density modulation of a crystal. And this already suggests two possible ways to approach the problem of supersolidity. And the first approach is to start from a solid and to look for superfluid phenomena possibly exhibited by the crystal. This was the idea of the first works in the field. In particular, I would like to mention the famous paper by Leggett in 1970. The title of the paper was Can a Solid be Superfluid? This work and other important papers written in this period stimulated the interest of experimentalists of solid helium who tried to look for superfluid phenomena, in particular exploring the rotational properties with an oscillator, rotating oscillator within the crystal. And unfortunately, these experiments, despite the fact that at the beginning they seemed to provide promising features, that at the end were revealed to be wrong because of a wrong interpretation of the thermal effects in the system. At the end, finally, the results were rather disappointing about crystal helium-4, which is not believed anymore to exhibit superfluid phenomena. This is the way to look for superfluid phenomena in a solid. The alternative possibility is instead to start from the superfluid and to look for possible solid behavior exhibited by the superfluid. And from this point of view, one can rephrase the title of Leggett's seminal work in a different way, an alternative way. Can a gas behave like a crystal? Why I'm speaking of a gas? The gas I have in mind ultracold gas, which in the case of boson in particular, exhibits Bose-Einstein condensation and superfluidity. And the question is that since in this system it's possible to tune in a very good way the interaction and the trapping conditions, and mainly since the formation of spontaneous formation of density modulation is associated with the clusters which contain many atoms as typical sites of the crystal. This makes a big difference with respect to standard crystals, where we have only one atom, and so the possibility of generating coherence among the sites is much more improbable with respect to the case of a fluid, of a superfluid. And in particular, this possibility is now represented in this image. This is one of the images, the first images obtained, where the typical fluid, which is without crystallization, spontaneous crystallization, would be uniform can exhibit this spontaneously, this density modulation, which involve a large number of particles per site, and consequently favor in a natural way the formation of coherent configuration. So you have at the same time the possibility of exploring spontaneous density modulation, or crystal features, and coherence, which is typical feature of supersolidity. At this moment, there are at least 3 platforms that have been very successful in generating supersolidity. So the spin-orbit coupled VCs that were for the first time obtained in the supersolid phase in a seminal paper by Vatican Ketterle, and then the dipolar gases, which is probably is the main topic of my next slides, and also by BAC in optical resonators. In the following, I will present some results on the supersolidity in ultracold dipolar gases, where the experimental activity has been particularly rich in the last 5 years, and both from an experimental and a theoretical point of view. And these are some collaborators with whom I shared my scientific activity more recently, and also less recently in previous scientific collaboration, also with experimental teams in Florence and Pisa, and in Stuttgart, in particular concerning cell-bound droplets. But let us consider the main feature of the interactions in a dipolar gas. One can identify 2 important features in the interaction. A short-range nature of the interaction, which can be represented with the contact interaction, and is expressed in terms of the scattering, S-wave scattering length, as a typical relevant parameter, and the real dipole-dipole interaction, which is long-range and contain both attractive and repulsive components. And this dipole interaction, of course, is produced by atoms which contain some magnetic moment, and this is the case, the most popular case in our field and in this moment. Of course, the great hope will be to produce atoms containing dipolar moment, but so far the experimental realization of this configuration is not has not advanced so much. Also, for the dipole interaction, one can introduce a typical length, which is called the dipole length, and the ratio between this dipolar length and the scattering length represent relevant dimensionless parameters, which provide a relative weight of dipolar and short-range sources. This dimensional parameter drives the transition from the superfluid to new phases exhibited by dipolar gases, and these are the main results that I will show later in my presentation. A first important point to characterize the nature of the interaction is that if you treat it at the mean field level, you have troubles if you increase too much the weight of the dipolar force because of the attractive nature of the interaction. And this gives rise to a collapse which destroys the system if you treat it using mean field approach. This problem has been solved by including, by adding to the mean field description a quantum fluctuation effect, which can be calculated and obtained by starting from the theory developed by Li Wang Yang correction to the equation of state. The final result is expressed in a new formulation of the Gross-Pitayevsky equation for these atomic gases, which contains, in addition to the two-body density interaction, also the effects of quantum fluctuations, which are crucial to establish the equilibrium properties also for large intensity of the dipolar force. And an important spectacular consequence of these quantum fluctuations is the possibility of realizing self-bound droplets, as was presented yesterday or before yesterday, I don't remember, by Tilman Pao in his talk. Self-bound droplets are systems which are self-bound, like in atomic nuclei, for example, or like helium clusters, and which represents a new beautiful phase of matter, which is not however the system that I am looking for, because here we like to study the supersolid, which is not an assembly of self-bound droplets, but it's an assembly of droplets which are coherently coupled, and this is the crucial point characterizing supersolidity. An important feature characterized by the dipolar force is the presence of a rotonic structure in the spectrum of elementary excitations. This feature was predicted in a very important paper by Luis Santos, George Lapnikov, and Maciej Levinstein, 10 years ago at least. And in particular, if you increase the size of the dipole interaction, you favor the formation of this roton minimum, which becomes smaller and smaller, and eventually becomes unstable, giving rise to what's called a roton collapse, and suggesting the idea that for larger value of the interaction parameters, you can reach the new quantum phases. And this brings an analogy with the physics of liquid helium, where we know that the minimum in the roton excitations is a precursor phenomena of the solid phase at larger pressure. In 2019, three experimental teams in Pisa, Florence, in Stuttgart, and in Innsbruck reported the first experimental evidence for supersolidity, revealing both the natural density modulation of this configuration, spontaneous density modulation, and the phase coherence, which are crucial ingredients characterizing the supersolid. And in this beautiful picture that was taken from a paper of the group of Stuttgart, you can see on the side, on the left side, the density modulation. On the right side, you can find the evidence for coherence, which is obtained by looking at interference patterns after expansion. After this fundamental achievement, 2019 is considered the year of dipolar supersolidity. And but at the same time, this was the beginning of a new investigation, scientific investigation, that I would like here to summarize here. In particular, the last 3-4 years have been devoted to better understand the superfluid features of this supersolid dipolar gas. And the focus has concerned the nature of Goldstone modes, which are typical consequences of the spontaneous breaking of some fundamental continuous symmetries, the deviation of the moment of inertia from the rigid value, and the realization of quantized vortices. I would like to very briefly show some results about the Goldstone modes. In particular, the real Goldstone modes take place in infinite matter, where I take the form of phonons, gapless phonons, and in the case of supersolid, there should be two Goldstone modes, because you have two spontaneously broken symmetries. And this was observed actually experimentally, because you see that when you increase the size of the relevant interaction parameters, you find that collective oscillations in harmonically trapped gases is split into two collective oscillations, one characterized by a crystal type of nature, where the position of these clusters oscillate in a in a collective way, and the other, well, the size, the position of the clusters remain fixed, but there's the density which is oscillating from one cluster to another, exhibiting a typical Josephson-like phenomena. And these two oscillations were observed experimentally, and similar experiments have been carried out the same year in the group of Tilman Pao and in the group of Francesca Ferleino, and in particular in the journal Nature, in the News and Views report, it was emphasized the importance of this result because of the new nature of sound propagating in this configuration. But let me skip the discussion moment of inertia because I have not time. But I would like now to address the last important point concerning quantized vortices, because quantized vortices represent one of the hallmarks of superfluidity and reflect explicitly the quantum nature of the problem, in particular because they carry a quantized amount of angular momentum proportional to the fundamental constant of Planck constant characterizing quantum physics. So the question, can a superfluid host a quantized vortex? We approach this problem theoretically by suddenly rotating a confined configuration in the supersolid phase, and above some critical angular velocity, you observe the nucleation of a vortex which tries to enter between the interstices of the droplet of the system and put itself in the center of the trap. This nucleation process is very different from the one that took place in the seminal activity in the standard basis, in particular in the group of Jean Delevan, where the nucleation of vortices took place via a strong quadruple deformation of the cloud. The interesting results that emerge from this analysis are two. One negative, that it's difficult to image the vortex because the vortex tries to put it himself in the region of very small density between the interstices, and consequently it's very difficult to image because when you image, there are no atoms practically there, but there is an empty area, a region, also without the vortex. So how can you identify in imaging techniques the vortex? Of course, you can use interferometric techniques, but not a direct measurement of the density profile. But the positive news from this investigation is that the angular velocity to generate the nucleation is much more favorable in the case of the supersolid, because exactly the vortex can easily penetrate inside. And then this suggests us to propose a protocol to nucleate and to observe it. And the idea is summarized here. You start from a superfluid with rotating the system at angular velocity, which is not enough to generate to nucleate the vortex in the superfluid, but is enough to generate the vortex in the supersolid. So when you ramp the interaction parameters and you enter the supersolid, you generate this vortex, but at this point you can go back to the superfluid phase and you can obtain the image of the superfluid of the vortex in the superfluid phase, but the vortex was created in the supersolid. And this protocol was actually implemented in the group of Innsbruck by Francesca Ferleino and collaborators. And here are the two relevant images that this group was able to obtain. So, if you stay in the superfluid phase, since the angular velocity is not large enough, you don't nucleate the vortex. But with the same angular velocity, you can nucleate it in the supersolid, and then you ramp back the system to the superfluid, and you can image it. And so this figure that you see on the right represents the first experimental observation of a vortex which was nucleated in a supersolid. This brings me to the conclusion, and the main point is that now dipolar Bose-Einstein condenser gases realize the long-sought phenomenon of supersolidity. And the second point, that the Gross-Pitayevsky theory, with inclusion of quantum fluctuations, is providing an efficient way to explain and to predict new experimental results concerning coherence, the Nobel-Goldstone mode, the moment of inertia, the nucleation of processes, and opening a new series of important perspectives in the field. In particular, there are many interesting questions that remain to be investigated, like the role of quantum fluctuation beyond the local density approximation, the role of supersolidity at finite temperature, the relation between the sound speeds and the superfluid density, so the measurement of the superfluid fraction in these systems, and the possibility of implementing ring geometry and creating configuration with persistent current in the systems. And in general, the investigation of superfluidity in other superfluid platforms like spin orbit, coupler gases, and possibly Rydberg atoms and lattice supersolidity. So this is the end of my presentation. And let me, I would like to show my last image with reporting some recent, very recent review papers on these topics. In particular, there is a recent review paper on experimental activity on dipolar gases written by the team of the team of specialists in the field, including Inman Powell. Then we wrote recently, we published recently a paper on dipolar superfluidity with more theoretical perspectives, and simultaneously there is another paper, a perspective papers in the field of supersolidity in the spin orbit case. And I would like just to show this image, because this represents one of the last image of Lev Pitayevsky in our PEC team in Trento. You know that Lev Pitayevsky passed away last year, and he played a crucial role when he decided to leave Russia and to come to Trento in establishing new interaction and collaboration with the whole international community. And so I think I like to express my gratitude to him with this showing this image. Thank you.